The James Webb Telescope just detected something impossible. What if the story of our universe, the grand narrative we've painstakingly pieced together over decades, the one that begins with a singular, explosive moment and unfolds over 8 billion years, what if that story has a fundamental flaw? Imagine for a moment that everything we thought we knew about the universe's earliest, most formative moments was incomplete, or even, dare we say, wrong. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has just beamed back images from the very dawn of time. Images so startling, so unexpected, that they've sent shockwaves through the astronomical community. It has spotted galaxies so ancient, so surprisingly massive, and so brilliantly luminous, that scientists are now faced with a profound, exhilarating, and slightly terrifying challenge: questioning the very foundation of the Big Bang model as we understand it. Hello, cosmic explorers, and welcome back to SciSpotlight, your front row seat to the universe, where science ignites curiosity and discovery reshapes our understanding of everything. I'm your host, and today, we are embarking on an extraordinary journey to the edge of observable time. We're diving deep into a jaw-dropping, paradigm-shifting discovery made by the incomparable James Webb Space Telescope. A discovery so profound, it might just force us to grab our cosmic history books and prepare for a major rewrite. Fasten your seatbelts because this is big. To truly grasp the magnitude of what's happening, let's set the stage. The James Webb Space Telescope, or JWST, isn't just another telescope, it's a time machine. Its massive gold-coated beryllium mirror, over 5 meters in diameter, and its incredible sensitivity to infrared light allow it to peer back through cosmic eons, capturing photons that have traveled for over 13 billion years to reach us. We're talking about seeing the universe as it was just a few 100 million years after the Big Bang, an era known as the Cosmic Dawn, when the very first stars and galaxies were just beginning to flicker into existence. In early 2023, and with increasing frequency since, JWST released a series of images and data that left astronomers speechless. These weren't just any images. They were portraits of galaxies dating back to a mere 300 to 500 million years after the Big Bang. Now, based on everything we thought we knew at this incredibly early stage in cosmic history, we expected to find, well, baby galaxies. Think small, faint, irregular blobs of gas and young stars, the cosmic equivalent of newborns, still struggling to coalesce, still finding their form. These would be the humble seeds from which the majestic galaxies we see today, like our own Milky Way, would slowly, painstakingly grow over billions of years. But here's the colossal twist, the observation that's causing all the commotion. The galaxies Webb has unveiled from this primordial epoch are anything but small, dim, or underdeveloped. They are shockingly mature. We're seeing structures that are astonishingly massive, packed with stars, and glowing with an intensity that suggests they are far more evolved, far more developed than our cosmological models predicted could possibly exist so early. Imagine looking into a nursery expecting to see infants, and instead, finding fully grown teenagers already well-versed in the ways of the world. That's the level of surprise we're talking about. Some of these early galaxies appear to be as massive or even more massive than our own Milky Way is today, after 13 billion years of evolution. And they're not just formless collections of stars. Webb is hinting at, and in some cases clearly resolving, distinct structures, perhaps even nascent spiral arms or disc-like formations, features that we believed took billions of years to develop through countless mergers and gradual accretion of matter. The sheer brightness also suggests a furious rate of star formation, or perhaps even the presence of exceptionally massive stars, far more luminous than those typically found in later epochs. These are not the faint, struggling protogalaxies of our textbooks. These are cosmic behemoths appearing almost fully formed in the universe's infancy. This is like finding a fully constructed skyscraper just a few weeks after laying the foundation. It simply shouldn't be. So, why is this such a monumental problem? Why can't we just say, oh cool, early galaxies were bigger than we thought? Because this discovery strikes at the heart of our standard model of cosmology, the framework known as lambda cold dark matter, or LCDM. For decades, LCDM has been remarkably successful in explaining a vast range of cosmological observations, from the cosmic microwave background radiation, the afterglow of the Big Bang, to the large-scale structure of the universe, the cosmic web of galaxy clusters and voids. A cornerstone of the LCDM model is the concept of hierarchical structure formation. It posits that galaxies grow slowly and gradually. In this picture, tiny fluctuations in the density of the early universe amplified by gravity cause dark matter, an invisible, mysterious substance that vastly outweighs normal matter, to clump together, forming what we call dark matter halos. These halos then acted as gravitational wells, attracting ordinary baryonic matter. This gas would cool, condense, and eventually ignite to form the first stars and small proto-galaxies. Over cosmic timescales, these smaller structures would then merge and accrete more gas, gradually building up into the larger, more complex galaxies we see around us today. It's a bottom-up process. Small things form first and then combine to make bigger things. Think of it like building a magnificent Lego castle piece by piece, slowly and methodically. The galaxies Webb is seeing are so massive, so early, that there simply doesn't seem to have been enough time for this slow hierarchical process to have occurred. According to LCDM, the universe at 300 to 500 million years old should not have been able to assemble such colossal structures. The observed rate of galaxy formation, or at least the appearance of these mature giants, seems to be up to 10, 100, or in some extreme interpretations, even more times faster than our most generous LCDM models allow. This isn't just a minor discrepancy that requires a little tweaking of parameters. This is a fundamental challenge. It's like our meticulously crafted instruction manual for building the universe suddenly has a glaring error on one of its earliest pages. If galaxies can form this big, this fast, then either our understanding of dark matter's role, or the efficiency of gas conversion into stars, or the very timeline of the early universe needs a serious reevaluation. This is a potential crack, and a significant one, in the very foundation of how we understand cosmic evolution. It suggests that there might be crucial physics, fundamental processes, occurring in the early universe that are entirely missing from our current theories. Naturally, the scientific community isn't just throwing up its hands. This is where science truly shines. When faced with a puzzle, the race to find explanations begins, and the creative intellectual engines go into overdrive. Astronomers and theorists around the world are scrambling, proposing a fascinating array of possible solutions. Dark matter isn't behaving as expected. Perhaps our understanding of cold dark matter needs refining. What if dark matter isn't entirely cold and collisionless? Could there be forms of dark matter interactions we haven't accounted for that could accelerate the collapse of structures in the early universe? Some theories suggest warm dark matter, or self-interacting dark matter, which could lead to different seeding patterns for galaxy formation. Or maybe dark energy, the mysterious force accelerating the universe's expansion today, behaved differently in the early universe, influencing structure formation in unexpected ways. A new era of super-efficient star formation or top-heavy initial mass function. Could it be that the very first generation of stars, the hypothetical population 3 stars, composed almost entirely of hydrogen and helium, were far more massive and formed much more efficiently than we thought? If these primordial stars were hundreds or even thousands of times the mass of our Sun, they would have burned incredibly bright and lived short, explosive lives, rapidly enriching their surroundings with heavier elements. This is sometimes referred to as a top-heavy initial mass function, meaning more massive stars formed initially than we see forming today. Or perhaps starburst activity in the early universe was far more intense and widespread than previously imagined, converting gas into stars at an unprecedented rate. Primordial black holes as seeds. An intriguing and somewhat more exotic possibility involves primordial black holes. These are hypothetical black holes that could have formed directly from the collapse of overdense regions in the very early universe, long before stars even existed. If primordial black holes were abundant enough, they could have acted as gravitational seeds, rapidly accreting gas and dark matter, effectively jump-starting galaxy formation, and even the growth of the supermassive black holes we see at the centers of most large galaxies today. This could explain not only the massive galaxies, but also the early appearance of quasars, which are powered by these supermassive black holes. Are our cosmic age or expansion estimates off? The Hubble tension. Revisited, this is perhaps one of the more radical yet increasingly discussed ideas. What if the universe is actually older than the currently accepted 13.8 billion years? Or what if the expansion rate of the universe, encapsulated by the Hubble constant, has varied more significantly over cosmic time than our models suggest? There's an ongoing debate in cosmology known as the Hubble tension. where different methods of measuring the current expansion rate yield slightly different results. If the early universe expanded differently, or if its total age is greater, it could provide more time for these large structures to form through more conventional means. Some theories, like tired light, or models proposing evolving dark energy, could fundamentally alter our cosmic clock. If these early galaxies are indeed as mature as they look, and formed at redshifts of 10 or higher, giving them more time by pushing back the Big Bang itself would be a straightforward, albeit revolutionary, solution. Observational bias or misinterpretation? Scientists are, by nature, skeptical. Could there be something about how we're observing these objects or interpreting the data? Perhaps these galaxies are incredibly dusty, making them appear redder and thus older than they truly are. Or maybe the way we estimate stellar mass from brightness at these extreme distances and early epochs needs recalibration. However, the sheer number of these impossible objects being found by different teams using different analytical techniques makes this less likely to be the sole explanation, though it's always a factor to rigorously check. The truth is, it could be a combination of these factors, or something entirely new that no one has even conceived of yet. That's the thrill of it. So, where do we go from here? The first and most crucial step is more data, and thankfully JWST is a veritable fire hose of cosmic information, with new observations and deeper insights pouring in practically every week. Astronomers are already planning and executing follow-up observations of these enigmatic early galaxies. This will involve spectroscopy. This is key. By spreading the light of these distant galaxies into their constituent colors, astronomers can confirm their distances with much higher precision. More importantly, spectroscopy can reveal the chemical composition of these galaxies, what elements are present, and in what abundances. This will tell us about the types of stars they contain and how many generations of stars have already lived and died within them, giving crucial clues to their true age and evolutionary state. Deeper imaging, pushing JWST to its limits to find even fainter, even earlier galaxies. Are these massive galaxies the norm, or are they rare exceptions? How far back can we find them? Refining models. Theoreticians are already hard at work, running new simulations, tweaking parameters in LCDM, and developing entirely new cosmological models to see if they can accommodate these early behemoths. This is a dynamic interplay between observation and theory. Observations challenge theories, and theories guide new observations. We are, without a doubt, entering a golden era of cosmological discovery. It's a period where textbooks may genuinely need to be rewritten. What we thought was a fairly complete picture of the early universe now has some very intriguing, very large, unexpected brushstrokes. And the exciting part? It's young minds, perhaps some of you watching right now, who might lead the charge in figuring out this grand cosmic puzzle. The students and early career researchers of today will be the ones to analyze the deluge of JWST data, to propose the novel theories, and to ultimately reshape our understanding of where it all came from. This isn't a crisis for cosmology, it's an incredible opportunity. It's a sign that the universe is even more complex, more surprising, and more magnificent than we ever imagined. In the grand theater of scientific exploration, discoveries like this are the main event. They remind us that science isn't just a dusty collection of facts in a textbook. It's a living, breathing, evolving process of inquiry. It's not just about finding answers. It's about learning to ask better, deeper, more profound questions. The James Webb Space Telescope hasn't just shown us distant galaxies. It has opened a new window onto our own ignorance, and in doing so has illuminated the path to future understanding. The universe has just handed us one giant glittering mystery, wrapped in the light of its oldest stars. And you can be sure that SciSpotlight will be right here, following every clue, every new image, every breakthrough theory, to uncover what happens next in this incredible cosmic detective story. The quest to understand our origins is one of humanity's oldest and most noble pursuits. And right now, that quest just got a whole lot more exciting. If you're as fascinated by the mysteries of space, the thrill of scientific discovery, and the frontiers of human knowledge as we are, then make sure you don't miss a single update. Hit that subscribe button, give this video a like if it sparked your curiosity, and most importantly, share your thoughts in the comments below. What do you think is going on in the early universe? Are our models wrong? Is the universe older? Or is there some exotic new physics at play? We'd love to hear your theories. Stay curious, keep looking up, and stay tuned to SciSpotlight for more journeys to the edge of understanding. Until next time, clear skies.